Thank you so much, David. And thank you for inviting me to this little symposium before the board meeting. And I'm really happy to be here, and I'm glad I made it here. So it's like a correlated problem, which worked out. So today I want to tell you about some of my work on a new state of matter called a quantum spin liquid. And each word in that means something. So it involves spins. So these are magnetic materials that have local moments, and these moments interact strongly. And typically, this field has tried to get magnetic materials that have high transition temperatures. You want them ordering at high temperatures so they can be used for various applications. But quantum spin liquids is going the other way, where you want local moments, they interact strongly, but you don't want them to order. And you might ask, why would you ever want that? Well, it turns out these are not just paramagnets. These occur at low temperatures, and that's where the quantum comes in. So they are not ordering at low temperatures, not because of thermal effects that prevent the ordering, but because of quantum fluctuations. So that's the quantum in this new state of matter. And the liquid refers to the fact that the spins don't order, and hence they are. So I just got through the title. Okay, so that's the quantum spin liquid, but that's the most important part to understand, is that this is a new state of matter. And then what is interesting about it is that this seeming quantum paramagnet has very unusual excitations. So that's what I want to talk about. And what I will get to is that the traditional ways of observing magnetic excitations, which is neutron scattering, it does not prove to be useful here. And so I want to propose some new ways of detecting these fractionalized excitations. So I'm a theorist, so that's why it's very good if people here make materials or use different kinds of probes, because that's what we need. It doesn't move. Okay. So let me thank my collaborators here. So you can see there, Xie Feng is my graduate student who has now gone on to a postdoc at TU Munich. I have collaborations in India with Adip Agrawal and Shubhra Bhattacharya, in China with Tao Xiang and Kang Wang. And through all these collaborations, we are able to expand our tool set, because it's a very complicated problem and we want to get insights. So should I be localized here? Okay, I will. So we want to use multiple techniques because each one gives us a different kind of insight. And so we, as a result, our collaborations have expanded, and these are the different techniques we use. The latest work, which is unpublished, some on archive and some still unpublished, with Pengzhao Zhu, who's a postdoc, and Xu Yang, who's just returned to China, and Ryan Bukele, who's my current graduate student, with whom we have done some of the latest dynamical simulations. Okay, so the questions I want to ask: quantum spin liquids are a new phase of matter. Where should we look for them? What signatures should we look for? And why are we even interested in having such a material? And I won't get to this, but there is a very important pathway forward as a way to create anions. Excitations are anionic. They don't have boson or fermion statistics. And that allows us to braid them and create topological qubits that are different from the usual qubits in that these are error corrected. So you don't need to have like a bunch of 5 qubits in addition to your qubit that you're using to error correct. These are topological in nature, and that protects the quantum information in it. Okay, so you want to enhance the quantum fluctuations, so low spin, low dimensionality, and frustration, some kind coming either from interactions or from geometry that does not allow these spins to order. So you can see like triangles, if you have antiferromagnets on them or other more complicated structures, even in higher dimensions, can be a design source for such frustrated magnets. And they would typically have transition temperatures which are much, much lower than the interaction scale. So the very first signature, if you have a black pellet in your lab which looks promising, you're not going to start with spectroscopy. You're going to start with something like a susceptibility. And the very first signature would be, you would see chi as a function of temperature, then look at 1 over chi versus temperature and read off the theta Curie-Weiss. That gives an energy scale for how strongly the moments are interacting. And then you can look for TC. The best would be if you don't find TC and TC is 0. But even if that is not the case and TC is suppressed, you get a frustration ratio, which is theta over TC. And that is coming from one of these sources of frustration. So if F is large, that becomes a candidate quantum spin liquid material, because at least in this region in temperature between theta, which is somewhere here, and TC, the fluctuations can be strongly quantum dominated. Okay, and here are some long list of, this is certainly not complete, but you can see that the frustration ratio can range from of order, like 10 or so to almost several thousand. And so there are several candidate materials, and yet there are still a lot of material problems. There's disorder, there are other competing phases. So this field still needs a lot of work on materials. Okay, now as a theorist, one of the most fascinating things about quantum spin liquids is this single slide. We are used to fundamental entities that make up our materials like electrons. And in vacuum, an electron carries charge and spin. But remarkably, in materials like Mott insulators, the charge and spin can separate. So this can never happen in vacuum. It's only in an interacting system that you can get such a phenomena. And this is already very strange. But now we can see in spin liquids. So spin liquids are Mott insulators. They begin that way. So the charge has already on a very high energy scale, and the spin is at a low energy scale. But furthermore, the spin can also fractionalize into anions. That's what these, and I'll show you more examples of that. And the charge before us is to detect these fractionalized excitations, and in particular, see if we can find some ways to diagnose their sharp signatures in experiments. So I want to flash this very quickly. This won't be the topic of my talk, but this fractional quantum Hall effect is sort of the mother of these fractionalized states. It's a really simple system, just a two-dimensional electron gas created at the interface of semiconductors, and you put it in a magnetic field. And what that has done, initially, the Hall effect, which is 100 years old, says if you measure the transverse resistance as a function of magnetic field, it's a straight line. But as you raise the magnetic field, you get these plateaus. And as you keep raising it and the interactions become important, you get additional plateaus. And not just plateaus, the plateaus occur at odd filling factors. Filling factor is the ratio of the electron density to the magnetic field in units of the flux quantum. But there are also even fractions here that have all these properties of anions, fractional charge, abelian statistics, non-abelian statistics, everything just happens in this one system. And it's remarkable, it has this much richness. And today we see incarnations of all of this physics in graphene, which is even more tunable. Because at least in the quantum Hall systems, you needed systems with different densities, and then you could tune the magnetic field. But in graphene, by gating, you can tune both density and magnetic field. The reason I show this is there's been a lot of progress in this field on how to detect these strange excitations, like fractional charge using short noise, abelian statistics by interferometry, and even non-abelian statistics very recently using the fact that these states have states that carry carry heat on the edges, and these states have fractional thermal conductance. So there's all this progress, and the question is, can these or similar methods be applied to quantum materials? And that's where we need some dialogue. Okay. So coming back to quantum spin liquids, this is the traditional method of observing magnetism. You come in with a neutron, which excites a spin excitation. It flips a spin. So if you have a spin half system, it creates a change in your angular momentum by 1 h bar, and that forms a collective mode. So you have a collective magnon excitation, and that in spectroscopy shows up as a very sharp mode at a particular momentum and energy, and you can map out that dispersion relation. So that's what's shown in lanthanum copper oxide, which is an antiferromagnet. If you try to do the same thing in a quantum spin liquid, so this is a material alpha ruthenium chloride. This is not really the data on the material, but on a model which is supposed to describe the important interactions in this material. And then what you see, that same S of Q and omega, in scattering intensity, is extremely broad in momentum and energy. And the reason for this is because you have these fractionalized excitations. So the neutron is not creating a single magnon. That magnon is getting broken up into 2 additional fractions, let's say. And these fractions can now share energy and momentum in multiple ways. And that's why the spectrum has become broad. So what I want to do in this talk is go toward a new class of operators that you can try to measure. These are multi-spin operators. This is a single spin flip. So what we have found is that instead of focusing on single spin flip, if you look at 2 spin flips, they actually have sharp signatures that can be observed by NV centers that can measure noise and local correlations on some scale. We also propose through these multi-spin correlators that you can see braiding in pump probe nonlinear response. So that's kind of where I want to get to. But if you have questions, please ask. Okay, now in this topic, as I showed you, there are many materials and many kinds of interactions. I want to zero in on one particular model called the Kitaev model, because this model was solved by Kitaev exactly, and those kinds of models are very valuable. It gives us an anchor point from which to then launch into different directions. So this model is defined on a honeycomb lattice, and what you have at each site is a qubit. So this could be a spin half, or if you have spin orbit coupling, then it could be an angular momentum J half object at each site. And they have very peculiar interactions. On each bond, they have Ising interactions in different Pauli matrices. So we'd say the blue bonds involve sigma x, the green ones involve YY, and the red ones are ZZ. So these operators don't commute, and that is the source of the frustration. So if you look at any one qubit here, you can see it is getting 3 very contradictory instructions from the 3 neighbors telling it where to order. X or Y or Z, and that is the cause of the frustration here. So there's no geometric frustration, but the frustration is coming from the interaction. And the result of that is that these local moments don't order. That was shown exactly. In fact, they have something called topological order, which introduces long-range entanglement in the ground state. And the excitations of this model are fractionalized. And I want to focus on the entanglement aspects are also very important, but they are much harder to observe experimentally. So I'm going to go toward the excitations and pathways to experiments. Now, you may think this model is so artificial, it'll live only in theory land, but thanks to Jacqueli and Kalulilin's insights, they were able to come up with a design principle. So that's another important thing in quantum materials. You can't be digging these out of the ground or arbitrarily synthetically making them. You need a design principle, and that is what they came up with. And it's basically, you have these two rutheniums, and they are in an octahedral cage, and these cages share an edge. Okay, so they're not a corner sharing. If it's corner sharing, it would have created a Heisenberg exchange, which is isotropic, but they are sharing an edge. And that edge creates this kind of a two pathway for exchange, the upper and the lower. And remarkably, because of interference, let's say if this is the plane and my Z is the normal to that, then the two pathways will cancel the X and Y and only leave the Z interaction. So that's the origin of the Ising interaction on one of the bonds. And similarly, the other bonds have a different plane that is normal, giving rise to these separate Ising interactions. So this was their idea of using spin-orbit coupling and edge-sharing octahedra to create it. And then indeed, alpha ruthenium chloride is such a promising material. It does have additional interactions, and I will show you the ideas I'm proposing are remarkably not affected by that. It does affect the ground states you get, but if you can get out of that by applying some fields, then the observation of these fractionalized excitations still works. Okay, now that's the material platform. What is important today is if we want to connect models, we really don't care where they get produced. It could be in a material, it could be in a synthetic platform using Rydberg atoms. And here, without using spin-orbit coupling, using Floquet engineering, you can again create such models. So it's very useful to have all of these platforms working together to test and push different ideas. Okay, now I want to point out how this frustration gives rise to fractionalization without going into all the mathematical details, just through some pictures. So we already discussed how this spin is frustrated, and the result of that is it tries to get out of that frustration by making some smaller pieces that we call anions. So these 4 anions here. And furthermore, these anions then lead to some emergent new degrees of freedom. So say the green ones link up and so on. And if you go around a plaquette, that's like your electromagnetic A dot dl, you get a flux through the plaquette. And the 4th one, which is this black Majorana, that is left as an itinerant Majorana. So you get fluxes and itinerant Majoranas as a consequence of this fractionalization and the creation of new degrees of freedom. And this is a theme for all frustrated systems. Basically, frustration is localizing your degrees of freedom. Those spins are unable to make these magnons and these extended mobile magnetic excitations. That's not happening. So a new way of delocalizing some degrees of freedom and leaving some others localized. So what you end up getting is matter in the presence of gauge theory. And that's a very general feature. So now what is our prediction? So let me put it here in a table. So if you have a Heisenberg ordered magnet, I already told you it has sharp excitations when you perform a single spin flip. And the Kitaev, which is this model that I showed you, has broad excitations when you do the same experiment with a single spin flip. So we go to 2 spin flips. So here you're in your ground state. You flip 2 spins at time 0. You flip them back at some time t, and that you look at the spectrum. And that in a Heisenberg magnet or ordered magnet is broad because it creates 2 magnons. But surprisingly, in the Kitaev magnet, these are sharp and directional. Okay, now why does that happen? I'll give you a flavor for that. No, this is true in various parts. I'm no longer in just the Kitaev. I've gone away from that by adding a field also. Yeah, I'll show you. So I'm not using integrability. We use various ED, DMRG, and so on. And let me tell you the idea behind that. Okay. So what I'm going to do, just as Subir asked, this is the integrable point that Kitaev solved exactly, but we add a field and we also can add strain to the system and make one of the bonds stronger than the other. But then you get a very complicated phase diagram in such a simple model. So what happens is these Majoranas open a gap, and then when you start adding an additional field and you keep increasing the field, you might have expected the system will just get ordered, completely polarized at high fields. But what we find instead is that it goes through an intermediate gapless phase. I'm not going to go into all that. I want to just highlight how these 2 spin flips are giving you sharp excitations. I'm going to show you some results here, and also in this region here at high kz compared to kxy, where I showed you have matter and gauge degrees of freedom. It's useful to simplify the problem and gap out, let's say, the matter degrees. And now you only have the gauge degrees of freedom and understand some limiting cases. So again, I don't want you to go into all the details here, but just to get the idea. So the idea is very simple. When you do 1 spin flip, and then it, as I said, it mixes your fractionalized objects. In this case, fluxes and Majoranas get mixed up. Now, so I'm showing that here. I have done I've done a sigma plus or a sigma z here at this site. It creates Majorana and 2 fluxes in the 2 adjacent plaquettes. And when you do another sigma z here, that by itself also creates a Majorana and 2 fluxes. But now when you create 2 spin flips or 2 sigma z's, then it creates 2 Majoranas and 2 fluxes in each plaquette. But this theory, this gauge theory, is what is called a Z2 gauge theory, which means it allows fluxes which are 0 or pi. And if you have 2 fluxes, 2 pi becomes equivalent to 0. So you've managed to erase one of the degrees of freedom, which is my fluxes. And now you're left with just with a pure Majorana response. Similarly, if you go into the gauge sector, you still have 2 Majoranas here. I'm coming to that. So you'll see that. Yeah, you're tracking with me very well. So I'm not at the integrable point. I've shown you how you can erase 1 degree of freedom. And now I'm going to show you why they are sharp with a little animation. And I can tell you more details later. So let's say I'm not showing you the 2 Majorana part. I'm going into the gauge sector. I have a nice animation there, but similar things will happen here. The short answer will be that you will always have 2 anions, but unlike the 2 magnons, which could move independently, here there will be some gauge constraints constraints which will force them to move in a coordinated way. So actually, let me show you the animation. So are you standing up? Because I'm... Okay. Oh, I didn't realize I'm that slow. Okay. So here is, let's say in the gauge sector, I have two kinds of anyons. And these anyons are, you can think of them as a charge and a vortex. And so these anyons, if they were moving independently, it would have been a broad thing. But you look at how they move under the action of a field, they move in a very coordinated way, like this. And the result of this coordinated motion is that you get so if you look at a particular energy where these anyons are existing, you fix your energy and look in momentum space, you get this very particular linearly dispersing spectra. Okay, in the last -1 minute, let me just say one other key thing we have found, which is we don't just want to fixate on the fractionalized excitation and their charge and so on. We also want to see what is the braiding character. And using now, so this model, this Kitaev model, has this, and I showed you the E and the M anion which move together. If an E moves around an M, that's like a charge moving around a vortex, that behaves like a fermion. So if E moves around E, it acts like a boson. M moves around M, it acts like a boson as well. But if E moves around M, it acts like a fermion. So can we see this difference? And I'll just show you this one last slide, which is the following. So you do now a pump probe spectroscopy in which you first, this is the sequence, sorry. You first pump your system into an excited state with that red pulse. Then you perturb the system at a later time with the blue pulse and measure at an even later time when you do the measurement. Okay. Now, the result of that is that the first pulse depends now on how you pick your magnetic fields. If the magnetic fields are all in the same direction, that's the no braiding situation. But here I'm having magnetic fields in the X, Z, Z, X. That's very important. So the first magnetic field creates two vortices. The next one creates two charges. And then they braid for some time. And this braiding then has a signature in the response, which is very particular, shown here. So without braiding, as a function of time, this nonlinear response has a sinusoidal behavior and a decay. With the braiding, there's an additional term which grows in time, at least till the anyons are coherent, but there is a term which grows in time. And that is a very key signature of the braiding, and at least in this case, the abelian braiding. So let me not take more time. Let me end by saying that quantum spin liquids is a very exciting frontier, especially given both platforms, materials and synthetic platforms. And it's very important to push for new probes because the traditional ways of seeing these magnetic excitations don't necessarily give anything sharp. And we have these two suggestions which need to be pushed more experimentally. And moreover, this is on the magnetic side. These strongly coupled models also have analogs at weak coupling, and that's where they connect with flat band systems. So with that, let me thank you for your attention.
Nandini, very nice talk. My question is about the material side. I think one of your slides lists many material to be quantum spin liquid. Do you mean just the candidate or any confirm this quantum spin liquid beyond the one dimension?
So at this point, this was those authors who wrote the paper. I can go back, but they have, if they saw a large frustration ratio, they kind of put it in the spin liquid category, but it needs a lot more verification. So at this stage, like ruthenium trichloride has additional competing interactions which prevent it from being a spin liquid. And so my point was just, even if that is the case, the look in the temperature scale above Tc, below theta, and there at least start with those signatures. But a lot more things need to be verified. And particularly what should be looked for is the question. So at this stage, people do neutron scattering, and if they see broad features, it becomes a hopeful spin liquid, but the verification is still needed.
Yes, I'm just trying to understand a little bit the experiments you have in mind. So are we thinking about a pulse of electromagnetic radiation that in a non-frustrated system would be absorbed by a magnet? So and are you thinking about a kind of two pulse as a function of delay? And how are you thinking about probing this? So let's say you do this experiment. Yeah.
So this
how are you measuring? So what's the measuring pulse?
That would be just, you would detect, so you're sending in like a pulse of magnetic, either electric or magnetic field, second one, and then you're going to detect that electric field. You have detectors. This is in the terahertz region. Gigahertz.
I can understand the first two, but what's the third one? How you detect?
Well, I'm a theorist, so I propose the correlation functions, yeah. But these experiments have been done on standard magnets, and there's the whole field of, so you do a Fourier transform in terms of omega T1 and omega T2, and that's two-dimensional coherent spectroscopy. I'm not answering your question, but what I'm saying is you can make these 2D coherent spectroscopy maps and get signatures there. What we are saying is not to go to the Fourier space, to look in time for that very particular signature, which was that growth in time, that signature of braiding. And there's a beautiful paper by Parameshwaran. I had it on one of my slides here, which has some of the ideas behind why this happens. And it has to do with the braiding area subtended by these anions.
Online, really interesting discussion. Could we apply your model to quantum gates for benzoic molecules using the Hartman Hamiltonian?
Which Hamiltonian?
The Hartman.
I guess I have to find out more about that Hamiltonian.
Sure.
But you can make, the toric code, which is what I was showing, the Kitaev model at one limit becomes a toric code. So the toric code has been made with quantum gates. And they have also managed to, by measurement, create non-abelian states. So that is a very promising direction as well. Yeah. But I'm not familiar with that model. Yeah.
Thank Nandini again.
Thank you.